Hey everybody, welcome back to Environmental Organic Chemistry with Dr. Lisa. Today we're going to be talking about photolysis, which is the subject of chapters 15 and 16 in the second edition of the Schwarzenbach, Geschwind, and Imboden textbook. And this is the last major topic of the semester, so woohoo, we're almost there. So we're going to talk about two types of photolysis. One is direct photolysis, where the chemical itself absorbs sunlight and goes on to react. And the other is indirect photolysis. This is where the sunlight interacts with other chemicals, not your chemical, interacts with other chemicals and causes reactive species to form that then go on to react with your chemical. So there's a lot of differences between direct and indirect photolysis in terms of the mechanisms, the products, the rates, and one of the most important differences is that most chemicals, with a pretty small number of exceptions, most chemicals can react via indirect photolysis. But the number of chemicals that can react via direct photolysis is fairly small. So one of the things we're going to talk about is which chemicals can react by direct photolysis and which chemicals can only react by indirect photolysis and which chemicals just don't photolyze at all. So to do this, I'm sorry, but you have to know a little bit of molecular orbital theory. I'm sorry, I tried to get around it. There's really no way to do it. All right, so we have to remember from your organic chemistry class that there's different types of orbitals. And for our purposes, for most organic chemicals, we're only going to have to deal with three types of orbitals. We've got sigma orbitals, which are single bonds. We've got pi orbitals, which are double bonds. And we have n orbitals, which are non-bonding. Often they are lone pair electrons. And then in molecular orbital theory, all of these bonding orbitals have to have their evil twin, which is an anti-bonding orbital. So every time you have a sigma, you must have a sigma star. Every time you have a pi, you must have a pi star. Now the anti-bonding orbitals in most chemicals are not occupied. But the cool thing about photolysis is that we start to occupy that real estate and stuff starts to happen in those anti-bonding orbitals. Because what happens is when the chemical absorbs sunlight, or light at the right frequency, that causes electrons to move from the highest occupied molecular orbital to the lowest unoccupied molecular orbital. It's a game of musical chairs. The electron gets kicked out of its highest occupied molecular orbital. It has to go somewhere, and the best place for it to go is the nearest orbital, which is the lowest unoccupied molecular orbital. And so the kinds of transitions that typically happen in the environment and tend to be relevant are when you have electrons in the non-bonding orbital, like an n orbital, and then they can get kicked up into a pi star orbital. Or you have double bonds, in which case you have electrons in the pi orbital, and they get kicked up to the pi star orbital. So let's look at some molecular orbital diagrams. This is benzene. And so here's your bonding orbitals down here. These are the ones that are more stable, and so they're the bonding orbitals. So you have electrons. This is the pi cloud of benzene. So here's some bonding orbital here. So we have electrons in here. And then we also have these bonding orbitals that cover only 3 of the 6 carbons, but they're still bonding orbitals. And these is just the double bonds, right? And then above that, because we have these bonding orbitals, we must also have some anti-bonding orbitals, and that's shown up here. The most obvious example is this one up here, where each carbon has its own orbitals. It's not sharing electrons with any other carbon, and therefore not forming bonds. So in benzene, we have 6 electrons in this pi cloud, 2 here, 2 here, and 2 here. So they're all in the bonding orbitals, and they don't end up here in the anti-bonding orbitals. But again, under the influence of sunlight, something here, and this would be the highest occupied molecular orbital here, something here might get kicked up here to the lowest unoccupied molecular orbital. Here's another example. This is ethylene. Okay, so just 2 carbons and 4 hydrogens, and you can see all the different orbitals here. Some of them are, covering both of the carbons, and in this case, the entire molecule. And so it's a bonding orbital, but sometimes they're just localized on one carbon, so this is non-bonding or anti-bonding. So we have all of the bonding orbitals and their corresponding antibonding orbitals as we go up in energy. So in this particular molecule, the highest occupied molecular orbital is right here, and the lowest unoccupied, so this is the double bond between the two carbons, and then the lowest unoccupied molecular orbital is here. These are not shown in the order of their energy. They're just shown in, I don't know, some sort of random order. But so here's the highest occupied molecular orbital, where these electrons in this orbital are going to create a bond between the two carbons. But then if they get kicked up to this lowest unoccupied molecular orbital, they are no longer contributing toward creating a bond, the second bond, the double bond, between the two carbons. Okay, so how does this affect us? Well, there's a certain amount of energy it requires to get from the HOMO to the LOMO, right? And so the question is, does the sunlight that is hitting our molecule have enough energy to get our electron to move from the HOMO and the LOMO? Maybe it just doesn't have enough electricity. Maybe it just doesn't have enough energy. So how do we know how much energy is in a beam of sunlight? Well, the energy in the light is equal to h times nu. I know it looks like a v, but we pronounce it nu. H is Planck's constant. And so NV is the speed of light, c, divided by the wavelength. So we can relate the energy directly to the wavelength, because Planck's constant is constant here and the speed of light is constant. So the energy in the beam of light is directly related to its wavelength. So we can look at some bonds here that are typical for organic chemistry. And we can ask, well, how much energy does it take to break this bond? And then we could ask, what wavelength of light would we need to get enough energy that we could break that bond? Okay? So longer wavelengths of light will have less energy. That's because E is proportional to 1 over the wavelength, right? So longer wavelengths down here have less energy. Shorter wavelengths have a lot more energy. So the OH bond is quite difficult to break. It takes 465 kilojoules per mole. Now you might be saying, wait a minute, I know that we lose the proton all the time. In for example, like in a carboxylic acid, we lose that proton, we get the O with the negative charge, we have the conjugate acid, so what's the deal? Well, we're talking about homolytically breaking these bonds, and that's when each of the two atoms gets to keep one of the two electrons. And think about all the examples you know of in organic chemistry where oxygen gets to keep one electron and hydrogen gets to keep the other. There's like none, right? Because oxygen is extremely electronegative. It wants to hold on to both of those electrons. To take electrons away from oxygen, because it's so electronegative, is very hard to do, which is why this number is so big. So we need quite short wavelengths of light to get that kind of thing to happen. Carbon-hydrogen bonds, again, very stable. To pull off that hydrogen homolytically so that the carbon keeps one electron and the hydrogen keeps another is very difficult to do, requires a lot of energy, and therefore a very short wavelength of light. But some of these other bonds, not quite so much. CO bonds, a little bit weaker, little bit, still needs 330 nanometer wavelengths to get those kinds of reactions to go. But the carbon-chlorine bond, it's not weak, but it's not the strongest bond in the world. And so light with a wavelength of 353 nanometers is enough to break that carbon-chlorine bond. And in fact, it is true that for PCBs, which you know are my favorite molecules, for PCBs in the atmosphere, they do react with sunlight to start to lose some of their chlorines because the carbon-chlorine bond breaks. The bromine-bromine bond is an example of quite a weak chemical bond, bond energy of just 193 kilojoules per mole, and so even pretty long wavelengths of light are enough to break it. And the peroxide bond is notoriously weak. Each of those oxygen is desperately trying to hold on to its electron, and so they can reach a mutual agreement to homolytically split their bond and each keep an electron, and it's a fairly weak bond energy, and therefore long wavelengths of light are strong enough to do this. Now, what kind of light do we have hitting the Earth's surface? Well, what's hitting the Earth's surface is between about 200 nanometers and 600 nanometers. So that means that these bonds here are too strong. We're not going to be able to break them. We're not going to be able to photolyze them. Some of these bonds, could go. And then down here, these are quite weak and will react quite readily because sunlight hitting them has more than enough energy to break those bonds. So you might remember from your analytical environmental chemistry lab class that you did some spectrophotometry and you looked at the absorbance of different chemicals. And in your class, you related that absorbance that you measured in a spectrophotometer to the concentration of the chemical in solution. So you can do this for lots of chemicals. If they do happen to absorb light, you put them in a spectrophotometer, you hit them with the correct amount of light, and the absorbance is directly proportional to the concentration, and you can draw a standard curve and all as well. But you're asking, where did this come from? What's that alpha, which is a function of lambda? The parentheses here means alpha, which is a function of lambda. This here is sigma, or excuse me, epsilon, which is a function of lambda, not multiplied by lambda. So you're asking, where does this come from? Well, this is the absorption coefficient of the medium, right? And when you do spectrophotometry in the lab, you very specifically choose a medium that does not absorb at the wavelengths that you're interested in, so that you can ignore this part, right? You just go, forget about it, not going to worry about it, and you just worry about this, which is the absorptivity times the concentration times the path length, right, which is usually like a 1 centimeter cuvette. But in our world, in the world of environmental organic chemistry, we do have to worry about absorption by the medium. You know, because we have water. Water does absorb at some wavelengths. We've also got natural organic matter and stuff in the water, which definitely absorbs. That's why water that has a lot of gunk in it starts to look yellow or even brownish, because that natural organic matter is absorbing the sunlight. So our Beer-Lambert law is important. And so what it's telling us is that some of the light that's hitting is going to be absorbed by the medium here, and only some of it will be absorbed by our chemical. And we need to think about that. How much of the light actually is received by our chemical, and how much of it is screened out by the medium that we're in? Okay, so once our chemical actually absorbs sunlight, if it is available, if it's there, if it's freely dissolved, there's no natural organic matter that's screening out the light, let's say the sunlight actually hits the compound, and it has enough energy to kick that electron up into the lowest unoccupied molecular orbital. Well, then what's happening is that your compound, which we'll call C, is becoming C excited, which we're going to denote with a little asterisk here. So it's become excited, okay? That's great. But then what happens to it? Well, the dirty little secret of photochemistry is that mostly what happens to it is nothing. Mostly, the extra energy that this compound now contains is dissipated through physical processes, which just involve vibration, which means the solution heats up. Some things actually luminesce by emitting light, or you could transfer that energy to some other chemical in your system and photosensitize it. But in the end, the result is you still have your compound. It's still compound C, it hasn't changed. But for a small fraction of the chemicals that get excited up here, some small fraction of them will undergo a chemical reaction. It could just spontaneously fall apart into different fragments. It could rearrange. It could isomerize, which is kind of the same thing as rearranging. Or it could go abstract a hydrogen atom from some other chemical that might be floating by. Not from water, because remember, it's really, really tough to take a hydrogen atom with its electron away from water, right? Because oxygen is so electronegative. But other things, like natural organic matter, have carbon-hydrogen bonds, which are weaker. Let's go back to our list here. Remember, carbon-hydrogen bonds are weaker than oxygen-hydrogen bonds. So we might be able to abstract a hydrogen from oops, so, we skipped to the end. Sorry about that. We might be able to abstract a hydrogen atom from natural organic matter or some other organic chemical in the system. That means we take the hydrogen and its electron away. Dimerization, two excited chemicals knock into each other and form a dimer. Not very likely, because you'd have to have two excited chemicals, and maybe we don't have that much sunlight, but it could happen. And you could also have electron transfer from our chemical to some other chemical. And the end result is no longer is our compound C the same compound C. Something has happened to it. It has changed on a chemical level. So the proportion of our chemical that goes via this pathway, right, versus the total amount of our chemical that gets excited is called the quantum yield. And quantum yields are usually pretty low, like less than 1% of the chemical actually undergoes a reaction. And the magnitude of that quantum yield depends on the chemical structure very, very much. But it also depends on the solvent. It depends on the pH, the ionic strength, all kinds of things in the solution. And notice that, Schwarzenbach, Geschwind, and Imboden in this textbook is really aquatically centered. They're thinking about what's happening in the aquatic phase. And so when you read the textbook, it just spends a lot of time talking about what happens in water. But honestly, most of these chemical reactions are happening in the gas phase. If you can get your chemical into the gas phase, there's a lot more sunlight available when it's floating around in the gas phase than there is when it's in the water. So just keep that in mind. And then these reactions, because the sunlight has already provided the energy to excite our chemical, the rest of this, all this other stuff, has pretty low activation energies, 10 to 30 kilojoules per mole. So when we were looking at hydrolysis, we were seeing activation energies of 90 or 100 kilojoules per mole. But photolysis is not nearly as large because, again, all the energy for activation was provided by the sunlight. So that the heat, the background temperature, doesn't make that much difference. So these low activation energies mean that photolytic reactions are really not very temperature sensitive. They're sensitive to the amount of light hitting them, but not so much to the temperature. So here's some examples. Here's a chlorinated benzene, and it, because it has a big conjugated pi cloud, right? These are all pi electrons in here. Pi electrons. And then the chlorine here has these three lone pair electrons that three sets of lone pair electrons that you can't see. These are in n orbitals. So the fact that we have pi means that we also have pi star. I'm trying to draw with my mouse, it's not going very well. Pi star, which means that we can have a transition from n to pi star of a single electron. When we draw the movement of a single electron, we give it a one-headed arrow. So instead of drawing the second side of the arrow over here, I just give it a one head. So our molecule looks like this. So H nu here means that this is sunlight. So under the influence of sunlight, we get this n to pi star transition, and we end up with a radical on the chlorine. So the chlorine now is in a radical state. And free radicals do all kinds of interesting things. They can abstract hydrogen atoms. They might lose the chlorine. The chlorine could just pop off as a chloride independently, in which case you get a carbocation up here. You can't see it very well, but that's a positively charged thing. This is a carbocation. And either way, in both of these cases, you end up with phenol. So interesting things happening here. Here you're losing, the chlorine is actually abstracting a hydrogen atom from somebody else and then leaving as hydrochloric acid, and then the water is capturing what's left behind. So either way, you end up with a phenol. Here's another funky looking chemical. This is a nitrobenzene with some other funky stuff on it. So the remember nitro groups are kind of interesting. They have double bonds to the oxygen. Okay, and then they have lone pair electrons here and lone pair electrons here. So these lone pair electrons, of course, are in n orbitals, right? And this double bond implies that you have a pi and therefore also a pi star orbital, pi star. And therefore you have the possibility to undergo an n to pi star transition of one electron. And that's what happens here. So you get this funky radical here. And in this case, what you're going to do is this radical is going to go and attack, because right next to it on the same molecule, it has a place where it could attack and abstract a hydrogen atom. And so it's going to go ahead and do that because it's right there it's juicy. It's right there for the taking. It's like an apple right on the tree and you can't resist picking it. So then you've ended up with a diradical here. And if we count, we have 1, 2, 3, 4, 5. So if we made a circle of these, it would be a 5-membered ring. And that's pretty stable. Remember, in organic chemistry, 5- and 6-membered rings are quite stable. So we actually have rearranged this into a 5-membered ring. So interesting things happening. That's a molecular rearrangement. Here's an example of a ketone, right? Carbon double bonded to oxygen. The double bond means that we have pi electrons, and therefore we have a pi star orbital available. And again, this oxygen has 2 sets of lone pair electrons on it. And so you can have an n to pi star transition. So one electron stays on the oxygen, the other electron goes over to this carbon. And so you end up with this weird diradical. So this can do a number of things. One is that there is a hydrogen sticking out over here. available to be picked. So you could abstract that hydrogen, and that leaves something going on over here. So this pathway is where it's abstracted the hydrogen from something else in the solution, something that we're calling RH, and so we end up with an R radical over here. But it could also abstract that hydrogen from within the chemical and go through this pathway, and then you get the diradical, and the diradical could, if these two electrons got together, they would form a bond, and so they can actually form a cyclobutane here. Not a very stable structure, but not too bad. The other thing that can happen is, this electron goes here, one of these electrons comes in here, the remaining electron goes over here, and this electron comes in there, and what you've done is obliterate this bond right here and created two separate molecules here. So this is a fission or a breaking apart of the molecule. So all kinds of funky things can happen. And the moral of this story, this slide, is that when you form radicals, strange things start to happen. No one expects you to be able to look at the structure and say, I know exactly how that's going to react once it absorbs sunlight. All we're asking you to do is to recognize when a structure has both a pi orbitals and also n orbitals, right? Pi and n orbitals. That means that it is ripe to undergo some sort of direct photolysis because it can have an n to pi star transition. And those n to pi star transitions don't take a lot of energy to make them happen, and therefore they can happen at the normal wavelengths of light that are hitting the Earth's surface. So the next little sub-lecture here, we're going to talk about the rates of those direct photolysis reactions. So I will see you on the other side.